Viewers like you make this program possible. Support your local PBS station.
A mining lamp sheds light on a powerful, clean-burning engine.
Near zero emissions at the tailpipe. Think about that.
Highly conductive copper wire goes from communicating simple voices to complex electrical signals.
All it takes is one tiny bit of exposed wire or a missed connection to completely disrupt the flow of electrons, causing an electrical short circuit.
And tiny, ancient marine organisms create the building blocks for a supremely durable, aerodynamic body.
With diesel fuel being over $4 a gallon, every 1/10 of a gallon you can save is huge dollars.
Together, they create a highway workhorse that delivers vital products to every corner of the globe. Natural resources, critical moments in time, and human ingenuity forge the world's most awe-inspiring machines. From raw to ready. The highway truck. A heavy hauler essential to global business. In 1 year, a single big rig logs more miles than a typical car does in a lifetime. And carrying 160,000-pound payloads, they need to work in every condition. From sub-zero cold to triple-digit heat. To survive, they've got to be strong, durable, and fuel efficient, like the Mack Pinnacle.
This notion of durability, trucks that outlast any others. To deliver on that, you've got to build a really tough truck that can stand up to some of the most demanding environments on the planet.
These amazing endurance machines are made possible by 4 unexpected essential ingredients. Platinum, best known for expensive jewelry. It's a precious metal and catalyst in a chemical reaction that cleans engine exhaust to nearly zero. Petroleum, from million-year-old plants to a versatile new age material. Plastic, it's ideal for the giant engine hood and the transparent clear coat that protects the perfect paint. Manganese, a soldier's friend in the trenches. Now, the toughness behind the truck frame. And it begins with the soft, ubiquitous orange metal that electrifies the entire truck. Modern big rigs are packed with state-of-the-art technology for high-speed highway hauls. But what makes these road machines really stand out is their drive-by-wire technology. It replaces mechanical linkages with electrical signals that control everything from the clutch to the throttle. It's the same kind of system found in military fighter jets. To make this technology possible, engineers rely on one key raw material, first made famous as phone lines: copper. 1876. Alexander Graham Bell is experimenting with the first telephone. The lines he uses are made of iron or steel cable, and corrosion, rust, is a constant problem. He knows highly conductive copper is the ideal alternative.
The reason copper is so conductive is because the atoms are surrounded by a virtual sea of free electrons. A current can move through very easily. There's hardly any resistance.
But in 1876, the technology doesn't exist to manufacture copper cables strong enough for overhead lines.
Copper is hard to make into wire because when you pull on it, like this piece of gum, it thins in the middle. It's a process called necking. And what you need for wire is uniform thickness.
1 year later, And brass mill operator Thomas Doolittle thinks he has a solution.
His idea is pulling or drawing the copper through a series of smaller and smaller dies. This compresses the metal by a small amount, small enough that you don't need to heat the metal. And each time it goes through, the crystal structure is altered by the compression, making it not only longer, but stronger.
It works. The hard-drawn copper wire is both highly conductive and strong enough for overhead lines. Copper becomes the wire of choice for the telephone industry. Today, half of the copper we extract from the Earth becomes copper wire. And it all starts with a blast. Mining crews use explosive charges deep in the ground to blast copper ore into movable chunks. Each ton of raw ore yields only 12 pounds of pure copper. That's less than 0.6%. So separating the copper from its ore requires a special process called froth flotation. It begins by crushing the ore into a sandy powder. Then, the powdered ore is mixed with water and poured into a tank. To isolate the copper, xanthate salts are mixed in. They bond with the copper sulfide, making it hydrophobic or water repellent. Air bubbles are pumped into the bottom of the tank. The hydrophobic copper sulfide attaches to the bubbles, rising to the top as a copper-rich metallic froth. Workers smelt this metallic froth at over 2,000 degrees Fahrenheit, removing most of the remaining impurities to create copper slabs.
The copper slab comes out with about 99% purity. That 1% impurity means all the difference. Impurities are the biggest enemy. And it's simple. They interfere with the flow of electrons, causing resistance. So impurities don't really matter for a copper pipe, but in the world of wires, they mean everything.
To remove the last bit of impurities, technicians use a process called electrorefining. Workers submerge the copper slabs in an electrified acid solution for 10 days.
When an electric current is run through, the copper atoms come off the positive side and attach to the negative side, growing your very pure copper block. All of the impurities fall out to the bottom.
The copper is now nearly 100% pure. Finally, technicians draw the metal through a series of dies to create the precise gauge wire that's ideal for heavy haulers. At the Mack Truck plant in Macungie, Pennsylvania, superconductive copper wire goes to work, powering the drive-by-wire technology and every light, computer, and electrical accessory. It all happens in 3 steps. Assembly, where hundreds of copper wires are coded and organized. Cab wiring, where technicians outfit the cockpit with drive-by wire and every electrical control. And testing, a rigorous check of every wire and switch. In assembly, technicians begin by pulling individual work orders. Every truck is custom built. The build sheet is the Bible for the entire electrical system.
It tells me what I need to pick out to build a harness.
Next, workers create a custom web of copper cable called a wiring harness. This neatly bound maze of electrical lines protects the copper wires from shorting due to road vibrations, abrasion, and humidity. With hundreds of wires and connections, attention to detail is critical.
If
If you don't connect the right wires to the right things, the truck won't start. You apply the brakes, the brake lights won't come on. If you hook up one of the wires wrong, instead of locking the door, you could put the windows up.
A missed connection here could make it impossible to use the throttle and even apply the brakes. Safety is essential. That's why every single copper wire connection is checked and rechecked. Next up, cab wiring. On the line, the team mounts the critical rooftop accessories like lights, antennas, GPS, and horns. Using hundreds of feet of copper cable, a technician connects the drive-by-wire system and panel. These switches are the core of the truck's nerve center, and hundreds of connections all come back to this panel. They make it possible for the driver to control the throttle, transmission, GPS, and lights instantaneously with the flip of a switch or press of a pedal. Connections Thomas Doolittle couldn't have dreamed of when he first invented strong copper wire.
It really is attaching the brain to the parts. Any options that a purchaser wants, heated seats, push-button start, power door locks, things like that, I'll lay all the wires on that pertain to those items.
To keep all these vital connections organized, a technician goes beyond simple memorization.
My personal way that I've done it is I ask why. What is this wire for? Why am I doing this? And that's how I remember. There's one here for interior storage. This is the diagnostic plug so that the computer can plug into it in the dash to check the truck.
Then, operators carefully hoist the completed instrument panel into the cab and lock it into place.
We are now powering up the truck.
Next up, testing. Inspectors examine all the newly installed copper wire components and the drive-by-wire system. An expert technician plugs in a computer and sends electronic signals down every copper cable to check the wire and its connection. If the electrical structure fails this step, it's back to square one.
All it takes is one tiny bit of exposed wire or a missed connection to completely disrupt the flow of electrons, causing an electrical short circuit.
Checking turn signals. I check overhead lights, check the rear light, check windshield wipers, check the power mirrors, check the radio, check the heater, and check the horn. It passed.
The state-of-the-art drive-by-wire system's fully functional. A cutting-edge electrical nerve center on wheels, all thanks to mill operator Thomas Doolittle and the highly conductive metal, copper. The wiring transmits the commands that fire the engine, while this critical component ensures the emissions are surprisingly clear and clean. To pull 80 tons up a mountain, you need a 505 horsepower engine that generates 4 times the power of a normal car. But an engine like this also puts out more harmful emissions. These need to be cleaned before they exit the tailpipe. To do it, big rigs are equipped with a massive emission system that depends on one very special ingredient. Its unique property was discovered thanks to a life-saving lamp in the coal mines of 19th century England. Platinum. 1818. The English coal mining industry is in crisis. Miners are dying in underground explosions. The problem is open flames. Miners use them for light. And within the mines, when pockets of trapped methane and other highly flammable gases, known as fire damp, hit those flames, they explode.
Coal and methane are almost always found together, and that's because they're both produced from the same ancient plant matter, kerogen. While breaking up coal deposits, even a small pocket of methane can be extremely dangerous. It takes only 5% concentration to create an explosion.
The disasters prompt a plea to scientific organizations throughout Britain. The brightest minds go to work on the problem. And chemist Humphrey Davy believes he might have a solution that seems almost magical. He discovers that if he places a fine mesh screen around the flame, the light can pass through, but the flame doesn't ignite the dangerous fire-damp gases outside the mesh.
To create fire, you need fuel, oxygen, and heat. Around the lamp, you have fuel and you have oxygen, but the screen intercepts the heat.
Miners call the invention the Davy lamp, and it quickly goes into service in mine shafts everywhere. But in solving this problem for the miners, Davy also discovers something that will one day lead to a cleaner planet. He experiments further with the coal mine fire damp gases and the precious metal, platinum. He suspends a platinum wire over a flame and exposes it to methane. Predictably, the platinum in the flame glows hot. But after he blows out the flame, leaving just platinum and gas, the platinum continues to glow brightly. It's as if the fire damp gases are still burning, creating heat when the flame is gone. Davy has stumbled onto platinum's rare catalytic property.
A catalyst like platinum is something that speeds up the chemical reaction between other molecules. What Davy discovers is that the fire-damp gases and the oxygen interact with the platinum in the same way they interact with an open flame. This process of accelerating chemical reactions is called catalysis.
On a molecular level, methane and oxygen gas are attracted to the surface of the platinum catalyst, breaking apart as they interact with the metal. Then, as they release, the individual atoms spontaneously react to form new molecules, carbon dioxide and water. The reaction releases heat energy that turns Davy's platinum wire white hot. Over 125 years after Davy's discovery, the post-World War II economy is booming. Storefronts are going up, and warehouses are frantically shipping orders. But inside these warehouses, forklifts are spewing noxious gas that's creating toxic work environments.
One major exhaust gas is carbon monoxide. It's colorless and odorless, and it attaches to red blood cells in place of oxygen, so it can cause fatigue or headaches. In a confined space with enough of it, it can even kill you.
Platinum-based catalysis expert Eugene Houdry sets out to solve this problem. He experiments with 400 platinum-coated rods he calls CATs. He places them in the exhaust stream between the engine and the tailpipe, suspecting that the platinum will transform the molecules, just like they did over a century earlier in Davy's experiment. He puts this platinum to the test, and it gets to work on the gases.
It causes noxious gases like carbon monoxide and nitrous oxide to chemically react, transforming into carbon dioxide, water, and nitrogen gas. The really bad hydrofluorocarbons, or super greenhouse gases, react to form solids, so they get filtered out instead of exiting the tailpipe.
Houdry's design is a huge success, and his so-called CATs go into forklifts, cleaning the air inside factories and warehouses across the country. A decade later, Eugene Houdry turns his attention to the automobile and modifies his invention to work specifically on leaded gasoline engines. In 1956, he patents the catalytic converter. Surprisingly, though, it takes nearly 20 years for his invention to take off. That's when America's Environmental Protection Agency makes it mandatory equipment on every new car and truck. Today, the modern platinum-based catalytic converter is so effective that in certain areas of the United States, the air coming out of the tailpipe is cleaner than the surrounding air going in. An ideal emissions controller for a heavy hauling truck. At this powertrain facility in Hagerstown, Maryland, teams fabricate and assemble the components for a 505 horsepower, platinum-cleaned heavy hauler engine. Every component must operate within tight tolerances, or the engine will burn fuel inefficiently, creating unnecessary harmful emissions and more work for the platinum catalytic converter.
Near zero emissions at the tailpipe. Think about that. Today, you could take a white handkerchief, put it over the end of that exhaust pipe, and run that truck and take it down, and it would still look exactly the way it did, all white when you put it over that stack. It's pretty amazing.
Installing the catalytic converter takes 3 critical steps: engine assembly, engine mounting, and exhaust system installation. At the engine assembly line, technicians and robots work side by side, putting together this 3-dimensional puzzle, starting with the engine block.
This is actually the heart of the engine.
Next, robots install the cylinders and pistons. Throughout the build, inspectors check every component to ensure it meets exact specifications. The surface finish on the crankshaft needs to be within a 12-micron tolerance. The thickness of an average human hair is 85 microns. This inspector can't even be a hair off.
The tolerance is very crucial. It's very critical that if it's oversized, it would be too tight. If it's undersized, then it would cause all kinds of complications and noises in the engine.
Hoisting the camshaft into the engine, workers are careful to avoid touching the components with their bare hands.
Make sure you always wear gloves, because the salt and stuff from your hand, when they sweat, it can cause the camshaft to rust.
Robots complete the assembly by giving the finished engine a protective coat of paint. Next up, mounting. Back at the main assembly facility, technicians unload and prep the engines. Using an overhead crane, they carefully lower the engine onto its waiting frame. Now, it's time for the exhaust system and platinum-based catalytic converter. Compared to a car, this catalytic converter is massive, more than 4 times the size. And though from the outside you can't see the platinum, in this cutout you can clearly see the ceramic honeycomb that contains the platinum and other precious metals. Using an overhead crane, a technician drops the unit into place and secures it.
The exhaust comes out of the turbo on the motor, comes all the way into this guy, goes through its thing in there and comes out pretty clean.
The engine and catalytic converter are now ready for the open road, purifying emissions to nearly zero, all thanks to the Davy lamp and the powerful precious metal, platinum. The emission system knocks down dangerous pollutants, while this key ingredient lightens the load. Big rig engineers must constantly walk the line between heavy-duty toughness and cost-effective fuel efficiency. They've found the perfect balance in the material for the hood, It's extremely strong and resistant to dings and damage, yet it's extremely lightweight, and it easily molds into a streamlined aerodynamic shape. Hard to believe this critical ingredient comes from tiny ancient marine organisms. It's petroleum-based plastic. 300 million years ago, and dead organic material, like algae and even dinosaurs, is collecting on the bottom of oceans, riverbanks, and swamps. It's mixing with mud and sand, and more mud and sand.
Decomposing organic matter, buried deep in the earth and exposed to heat and pressure for long periods, turns into a dark, waxy substance that's rich in carbon and hydrogen, the building blocks for petroleum.
Millions of years later, in 1907, Dr. Leo Baekeland is looking for a new way to insulate electrical cables. He mixes a chemical derived from ancient petroleum called phenol with formaldehyde. The liquids react and become a hard yet moldable substance he calls Bakelite.
Bakelite is the first in a long line of petroleum-based plastics. Plastics begin with special molecules called monomers that link together into long chains called polymers.
Bakelite is the world's first synthetic polymer plastic, but it won't be the last. On its own, Bakelite's naturally brittle. To make it more resistant to cracking, it needs to be mixed with a filler, like sawdust, and this gives it an unattractive, dark, dull color. Fortunately, this is just the beginning. This new, versatile polymer science ultimately opens the door for thousands of unique combinations and techniques.
When creating polymers, you can make them long or you can keep them short. You can give them multiple arms. The sky's the limit. This type of versatility is what allows plastics to have such a wide range of physical characteristics.
Today, chemists have refined Baekeland's idea, creating plastic polymers for every application imaginable. From smartphones to the space shuttle, to the flexible, injectable plastic for the Mack truck hood. At Paramount Manufacturing in Abingdon, Virginia, engineers use plastic polymers to create the lightweight yet strong hood of this superhighway truck.
With diesel fuel being over $4 a gallon, every 1/10 of a gallon you can save is huge dollars. The lighter the weight you can make that product and still maintain durability, the better it is for the customer.
The manufacturing process has 3 steps: material testing, molding, and finishing. In testing, a technician pre-mixes samples of the 2 chemical polymers that react to form solid plastic. Checking the mix on a small scale now allows the team to verify the components are free of impurities before molding the hood. If there are impurities in the mixture, the polymer turns into the consistency of wet asphalt. If the batch is pure, the polymer hardens into a solid block that would make Leo Baekeland proud. After about 1 minute of stirring, the liquid begins to harden.
Curing occurs by the chemical reaction of 2 components, a resin and a hardener. When these are mixed, the polymers begin bonding, linking together in an exothermic reaction that releases a lot of heat. At its peak, it can be over 500 degrees Fahrenheit.
As the reaction begins to achieve completion, you see smoke start to come off of the cup.
This sample is rock solid, confirming the mixture is free of impurities and ready for production. The next step is molding. To form the hood, engineers use large shapes that come together like a clamshell.
Okay, as you can see, this would be the shape of the hood. And this would actually be the top of it. And here, if you would look, the customer would see this would be the wheel opening, and the wheel actually will go right underneath here. This would be actually like the fender for the hood, so it's all one component. The material will flow up here, and actually will spread out evenly, and it will flow through this runner, this gate, and actually evenly fill up at the same time all the way up into the mold.
Operators close the mold and inject the petroleum-based resin and hardener. As they mix inside, it's critical to avoid air pockets. One small bubble can ruin the entire part.
If you get air in there, it basically will stay as a liquid and it will not cure, will not harden at all.
To combat this, jets inject the two chemical components from the bottom up. This way, as the mixture rises, air escapes through the top instead of becoming trapped inside.
This works because of the nature of curing polymers. Curing takes time, and this allows the air bubbles to move up before the liquid turns into a hardened polymer structure.
The components combine, harden, and form the hood in under 2 minutes. Less time than it takes to fill up a tank of diesel. Once the plastic completely sets, operators open the mold and reveal the new hood. A smooth, perfectly hardened surface. The final stage is finishing. A robot glues small brackets and braces to the hood using industrial-strength epoxy. And then workers sand down the rough edges. The all-plastic hood is complete, an aerodynamic structural element made strong and light. All thanks to Earth's powerful brew, petroleum. The body's durable face and a protective coating that lasts nearly forever, both derived from the same remarkable raw ingredient, petroleum. For a truck to handle extreme road and weather conditions 365 days a year, it must have a solid outer shell to protect it from sun, snow, wind, and ice. Durable and transparent, it's a high-tech paint coating inspired by ancient insects. It's petroleum-based polyurethane. 1000 BC. Craftsmen from India and China are looking for a clear protective finish that they can paint on artwork and furniture. They find an answer in a resin secreted by lac bugs. It creates a shiny top coat that's naturally waterproof and sun-resistant. A few hundred years later, explorer Marco Polo sees this remarkable surface preservative and brings it home to Europe. It takes off as a protective layer for paintings, furniture, and wood carvings. Shellac.
UV or ultraviolet light has just the right wavelength and energy that it breaks the bonds between polymers, causing things like paint to decompose over time. Shellac, which is a natural resin, has special molecules. When they're broken by UV light, they can rebond, becoming stronger. It actually makes the material harder.
The turn of the 20th century, and the world is looking for a synthetic shellac, a synthetic protective coating. Researchers like Leo Baekeland are experimenting with petroleum-based polymers. And in 1937, one of them, Dr. Otto Bayer, develops a highly adaptable synthetic polymer that can be engineered to be clear, colored, thick, thin, hard, or flexible. He calls it polyurethane. In the early 1980s, the automobile industry is making cars of every color. But they have a problem. Exposed to weather, dirt, road debris, and ultraviolet rays, these colors fade quickly and lose their shine. To protect colorful car paint jobs, scientists adapt Bayer's polyurethane to make a new protective coating. Unlike the plastic used to make the truck's hood, their polymer blend is transparent and flexible for coating paint. It's polyurethane clear coat.
What's great about man-made polymers is you can fine-tune them to do whatever you want. If you want a hood, you can use a rigid polymer that holds its shape. If you want a polyurethane clear coat that's going to show the paint as well as protect it, you just need to pick the right polymer.
Today, heavy haulers drive over 1 million miles in a lifetime. To endure the chips and scratches from daily road hazards and constant power washes with chemical industrial cleaners, polyurethane makes a clear coat that's extra tough for these durable road warriors.
Because polyurethane is the man-made version of shellac, it doesn't have the same weaknesses. The lac bug's natural polymer, shellac, is soluble in alcohol. But polyurethane is resistant to chemicals, including cleaners, that may harm the underlying paint.
At the factory, the paint team unloads a cab and moves it into position for color and protective surface. It's a 5-step process. There's painting, polyurethane clear coat, drying, inspection. And to start things off, operators prep and clean the cab bodies in a specially designed clean room. From the lint-free jumpsuits to the positively pressurized air, everything about this space is dedicated to forcing dirt out and keeping cabs free of dust and debris. The process is called tack-off, and it features a tacky cloth that technicians use to clean the entire cab from top to bottom.
All these jobs are important, but the dirt can be a big factor.
Next, it's time for a colorful layer of paint. The selection is completely computer controlled.
It's all computerized. They'll do a flush procedure, and then the next paint gets loaded over there in the vault.
Painters have less than 3 minutes to paint hoods and under 6 minutes for the cabs, all while using perfect technique to create a uniform finish.
Painting is something that you learn through time. You can't just pick up a gun and just do it. There's definitely a lot of practice, a lot of finesse, learning how the paint reacts, how it lays down, how it's going to flow.
Now, the polyurethane clear coat.
When you see the guy snapping the wrist, they're trying to keep getting too much product in one spot at the end of their panel. If they're not fanning it away, they're going to cause a run or a buildup of product, and then you're going to get imperfections.
The teams apply a layer that acts just like armor, protecting the metal cab from rust, road salt, sand, and degrading ultraviolet sunlight, all without the need for laboring lac bugs.
It's UV protection. It's what generates the shine, the deep gloss shine that you see on the final product.
Next, the line carries the trucks into an oven to dry for 45 minutes. The procedure starts at 133 degrees Fahrenheit and rises to 200 degrees to bake in the polyurethane layer. Finally, the cabs face the keen eye of paint inspectors. They check for any imperfections. One mistake and this cab will head back to square one. A seasoned inspector has to have a finely tuned eye.
I'm looking for any defects that there are on the paint, any bits of dirt, any sags, anything that will keep it from being a perfect job. And depending on which way you look, some of the things you don't see until you turn a certain way, and then they will glance off and you'll note that there's something wrong. This one's good. It's got some things wrong with it, but it's going to go into finesse and little ticks, and they'll take care of that.
With the paint and clear coat applied, this cab has a protective layer ready for a lifetime of harsh weather and road conditions. All thanks to ancient lac bugs, innovators like Dr. Otto Baer, and a high-tech petroleum-based ingredient called polyurethane. The protective coat provides strength to the exterior, while inside, the powerful frame takes the abuse and handles the weight. The backbone of this truck is a pair of immense steel rails. They must hold the payload and take the force from the heavy hauls, rough roads, and sudden stops. The critical raw material that makes this steel so tough, a World War I lifesaver, manganese. 1915, and the world is at war. Soldiers are sheltering in trenches, battling the enemy only a few hundred yards away. Head wounds from artillery fire and shrapnel are killing thousands and thousands of men. The Allied forces need a new, stronger material for helmets. They've been using mild steel, a simple alloy of iron and small amounts of carbon. But it's just not strong enough to stop the injuries.
Armor like helmets needs to be hard to resist the penetration of bullets. This can be done by adding a little bit of carbon into iron to make steel, but that can sometimes make it brittle. And the problem is that a powerful impact can then cause shattering and more shrapnel.
Then, English metallurgist Sir Robert Hadfield takes on the task. He experiments with metals to mix with iron, searching for the perfect alloy. He tries an ingredient that's not normally used for armor, manganese.
Manganese is a chemical element found in many minerals. For industrial purposes, it's normally used as an alloying agent with other metals. For steel, it's added to increase toughness, the metal's ability to deform without fracturing. It's a characteristic very important for armor.
The way manganese toughens metal is called twinning. Unlike mild steel, the layers are able to change position together. This allows the metal to deform more quickly, absorbing kinetic energy instead of breaking. The newly created manganese alloy helmets are much stronger. They protect against shrapnel and pistol shots from as close as 10 feet. The Allied forces quickly put the new helmet into service on the battlefield, saving countless lives and helping to win the war. Today, manganese-infused steel is used around the world in everything from bridges to skyscrapers.
The frame of a big rig experiences rough conditions, bending and twisting, hard knocks from potholes. Adding manganese to the steel frame increases its toughness, making it able to withstand this kind of punishment.
To make manganese-toughened steel, refineries start with a manganese-rich ore, like pyrolusite. They reduce the ore to 80% pure manganese and add just a tiny amount of the metal to 2400-degree molten steel. Then they pour the mixture into a caster. That shapes the metal alloy into slabs. These tough manganese steel slabs are then cut and formed into a variety of shapes, including the long, thick rails of the heavy hauler frame. At the plant, the manganese-reinforced frame becomes the backbone of this highway truck in 3 steps. Frame preparation. Assembly, where the frame is outfitted with all the necessary components for braking and electrical functions. And finishing, where workers seal the surface. In frame prep, technicians load the chassis onto the assembly line.
Hey, heads up!
And teams of 6 fly 50-foot manganese-reinforced frames through the air and position them precisely on the moving assembly track.
The chain in here keeps moving. Goes from here all the way down to the end of the plant. I'm gonna set it here on the dollies and the buggies for it to go down the line. That's the front buggy.
Using a wireless remote control, crane operators hoist the 5-ton frame. There's no room for error.
You're moving something about 4 to 5 tons, so yeah, you just have to be careful.
To link up with the moving chain under the floor, he must position the frame within inches of its target.
But it's amazing how accurate and general you can be with it for how big of a piece of frame that you're moving.
Now, in assembly, teams outfit the manganese strengthened frame with air hoses for the massive air-powered brakes. These brakes rely on the frame to endure quick stops of a 160,000-pound payload, stops that put tremendous pressure on the manganese-toughened frame. To ensure the airlines are installed correctly, the technicians use color coding that provides simple tracking for assemblers and truckers.
Each part has to be perfect, being that if I don't do it perfect here, even the next guy after me, he's gonna get affected because something's gonna be either in his way, it's not gonna be long enough, or it's gonna be short, or it's gonna be missing if I don't do it in the right manner.
Finally, technicians tape off the critical connections and give the entire frame assembly a coat of corrosion-resistant paint. This seals everything and protects the undercarriage against road debris, sand, and salt. With the last spray of paint, the frame is complete, ready to shoulder the weight and stop a 160,000-pound truck at highway speeds. All thanks to a World War I helmet, Sir Robert Hadfield, and manganese. Thousands of skilled technicians working day and night have turned 4 powerful raw materials into the essential parts for an impressive big rig. Now, it all comes together for final assembly. To begin, workers install the front windshield into the cab. In teams of 2, they seal the glass into place.
This does is when you pull this, the rope is inside the rubber on the windshield and it rolls the rubber out over the steel edge on the cab.
Then, they marry the front and rear sections of the cab. It takes 2 technicians to install all the necessary components in the rear of the cab, known as the sleeper box. Drivers spend hundreds of nights a year sleeping in their trucks, so this home away from home is equipped with everything you'll find in a modern apartment. It makes life on the road surprisingly comfortable.
We put refrigerators in some of them. There's inverters, park heaters. The truck doesn't have to run. They're parked along the road wherever the guy decides to stop, and he can actually heat the inside of the sleeper box with just a couple of drops of fuel and keep it pretty warm and toasty in there without running the motor.
The team uses an overhead crane to join the fully wired cab and sleeper box, creating the ultimate long-haul control center.
Everything around you is there for a reason. The driver environment is incredibly important to these guys because for some of them involved in longer hauls, it really is their home away from home when they're out on the road.
Crane operators fly the cab over to the frame line, where it's carefully dropped onto the manganese alloy frame. The team quickly goes to work, making all the vital connections and bolting it into place.
These are cab mounting bolts. They get put in loose here and they get tightened further down the line.
I'm tightening up the clutch. We're going to adjust the free play in a few minutes.
Now, workers prepare the wheels and tires. From long-haul highway runs to down and dirty logging roads, every job has a different wheel, tire, and tread requirement.
These are what they call a super single. Usually there's two sandwiched together on the back. This is more for a tractor application, more for pulling and weight on top. All green means good torque.
Finally, from attaching the hood all the way to the grill and mud flaps. It only takes a few hours for workers to assemble the remaining components of this highway hauler from the ground up. The Mack Pinnacle is complete, ready to take on the open road. Pulling onto the pavement, copper energizes the drive-by-wire system, giving truckers state-of-the-art controls. The manganese-strengthened steel frame provides toughness to pull 160,000 pounds, while plastic made from petroleum keeps the truck's weight down to lessen the load. Barreling down the highway, the polyurethane clear coat shields against constant road debris and relentless ultraviolet light. And platinum kicks off the chemical reaction that cleans engine exhaust to nearly zero.
We see these amazing hauling machines around us every single day, so it's easy to lose sight of how incredible they are. We completely depend on their ability to move food, gasoline, even other machines wherever they need to go, day in and day out. And it wouldn't be possible without the power of raw materials harnessed by human ingenuity.
From natural elements to the toughest big rig on the planet, the Mack Pinnacle. Built from raw to ready.